Hello again. Welcome back. My name's Bill, and today I'd like to talk about time. I'm seeing a lot of places on the internet that are asking, does time exist or not? Well, I think that that's a little bit of a complicated question, and I think we need to ask one question before we can answer the second. And that is, are you correlational information or are you causal information? That's going to be crucial on whether time exists or not. My hunch is that if you're correlational information, time does not exist. My hunch is that to correlational information, the universe basically appears like a singularity. There is no distance for correlational information. Now, causal information requires time. There has to be order, and there will be distance related to that. So those are two different types of information. You have to know which one you are to understand whether time exists or not. So let's dive into the correlational information and what that means. So when I'm talking about correlational information, I'm talking about entanglement. Say we have a prepared pair of particles, and before we measure, both particles are in a state of superposition, spin up and spin down. If we separate those particles by 1 billion light years, if Alice measures her particle and finds it to be up, Bob will measure his and find it to be down. As soon as the wave functions collapse, whatever that answer is, the other particle will assume the opposite spin. Now, this happens regardless of the distance. It's the same amount of time, whether these particles are picometers away or whether they're billions of light years away. Now, I'd also like to talk about Zeno's arrow paradox. A lot of people use this paradox to explain that time does not exist. So the paradox goes something like this. Say that you shoot an arrow and you snap an image of it. And then you give that image to somebody and say, where's the time in it? Looks like time doesn't exist. But I actually think that Zeno's arrow paradox proves time does exist. For one simple fact, length contraction. If that arrow is moving, its length has been contracted. And you can tell how fast it's going by how much it's been contracted. A 1 meter arrow launched at 0.8 c will no longer appear to be a 1 meter arrow to the observer. It will appear to be a 0.6 meter arrow. Not only can you tell time by the length contraction, you can also tell by Doppler shift. The part of the arrow that's coming towards you will be blue shifted. The part that's going away from you will be red shifted. So you can also tell direction. So you could tell the events immediately preceding the image. You can predict where the arrow was. And then also you can predict where the arrow will be in the events immediately following the image. So time is encoded into that image. It's just part and parcel of how space-time is configured through causal information. Now I'd like to talk about how these two types of information flow. So I think a good idea to help explain this is the holographic principle. So the holographic principle states that any 3D region can be defined by its 2D boundary. And every particle that's in our universe is smeared across the entire horizon. You could almost think of it like, let's say you had looking at one particle, and it would be like a large wallpaper with a repeating flower. And anytime that particle changed states, anything happened to that particle, the entire wallpaper would change. That flower would morph on every area of the wallpaper at the same time. That's how holography works. So in that case, if you have two particles that are separated by, say, 10 billion light years, on the holographic horizon, those particles are right next to each other. Now, even though they're right next to each other, causal information can't just jump right to the next particle. Correlational information can. Correlational information can jump that tiniest bit of distance to reach that holographic particle 8 billion light years away, or 8 picometers away. It's the same distance for correlational information. Now, causal information has to flow. So its information channel, if you have 10 billion years separation between your particles, it's going to take 10 billion years for causal information to flow from one particle to the other. And on the holographic horizon, it would probably look something complicated, like your flower would change shape and morph in shape slowly over 10 billion years until part of it connected with another particle that was on that same wallpaper 10 billion light years away, and then 10 billion years later. So that kind of explains how correlational information can jump incredible distances, because it does so on the holographic horizon. And I believe it's probably through ER equals EPR that a wormhole is created in 3D space, probably even on the holographic horizon, but it's structured differently there. But one of the other main arguments against time existing are the relative nows that are seen in relativity. And I think this causes a problem. I think that maybe the way they define synchronicity causes these problems. And what it suggests is that if there is a distant observer that's flying towards us, their now will be in our future. If that distant observer is flying away from us, their now will be in our past. Well, that doesn't sound too funky yet, but we know that our universe is larger than the apparent horizon of 13.8 billion light years away. We know it's about 92 billion light years across. So let's say that we have an alien 40 billion light years away, and he's flying away from us at 0.9999 C. That means he's going to cut a relative now slice almost 40 billion years into our past. Now, you see a problem with 40 billion years into our past for a universe that's only 13.8 billion years old? Yeah, that doesn't make a lot of sense to me, that somehow a distant alien can fly 3 times older than our universe before it began. We don't even know what was there before it began, but apparently the relativists think that, this is a doable thing. I don't think it makes sense. And when I've brought up this argument, relativists like to say, well, what sets the relative now then? So what sets the now then? What's the universal sense of now? How does the universe able to track, when now is? And I think it's pretty simple. The holographic horizon. Because if you change one particle state, then the entire horizon changes at the same time. So that event, if it precedes another event, then it'll be reflected on the holographic horizon. And this is how our holographic horizon is able to keep order. Now, I believe in a presentist universe, that basically every point in the universe is at its most current present, and then signals about what events transpired propagate at C. But basically order and sequence are preserved. And I believe that's because of the way the holographic horizon behaves. Well, this is some ideas on time, and I hope that some of you have some interesting ideas and could explain them to me. Go ahead and give it your best go, and let's try to, maybe together we can all find out exactly what time is. Thanks so much, and talk to you soon.